So we are going to solve some problems on AC sinusoidal circuits when these circuits are at steady state. That is, all the transients are gone, and each signal in the circuit is a sinusoidal signal. So when you're calculating, of course, different signals in the circuit, whether it's a voltage signal or a current signal, and when the circuit is at a steady state, then we go from time domain to complex frequency domain, from t as a function of t to the function of j omega. And all of our variables are considered as the variables in the complex frequency domain in the j omega domain. Once again, the methods, the laws, the rules that we are going to apply on any circuit, they are the same as you apply on DC circuits. That is, you're going to apply Ohm's law, voltage division, current division, combination of resistors in series, combination of resistors. In this case, it's not going to be just resistors, of course. It's going to be resistors and reactance correspond to inductors and capacitors. So combination of, let's say, impedance, combination of impedance in series, combination of impedance in parallel, and KVL, KCL, Thevenin voltage, superposition, all those things that we learned for DC circuit analysis are still valid for AC circuit analysis. So basic rules do not change. Again, the main idea is to analyze the circuit properly, write down everything after the analysis, write down what you are trying to find, write down the equations of those quantities based on the analysis and then the application of circuit analysis methods that you have learned. And when you have the equations written down, then of course you can use MATLAB, Octave, calculators, whatever you want to solve those equations, plug in the variable values and solve those equations. Again, I encourage everyone, as I've been doing it, is do not start putting values right from the get-go, because it's just going to make calculations more complicated, especially when you're dealing with complex numbers. And there are more chances of making errors. And there is no use to do that. I mean, there is a reason we learned algebra, and the reason is that it's always wise to use variables. And then plug in the values of those variables when you need to get your result. And MATLAB and Octave, as we've been doing, is the easiest way to solve things. Remember, not to analyze stuff. Analysis you still have to learn. And we've been learning those, the analysis for the last 10 weeks or so. But the main thing is analyze the circuit properly, write down the equations, and then we're going to solve those equations using MATLAB or Octave. As we've been doing, we have our small functions that are written in MATLAB. And again, use those functions because they just make life very easy. The parallel combination of impedance, the resistance parallel combination that you use, it's still going to be valid for parallel combination of impedance. And it's going to make life very easy, because again, when you are doing 1 divided by 1 over z1 plus 1 over z2 plus 1 over z3 plus 1 over z4, whatever, and you have complex numbers, if you start doing it manually, it's just going to be a pain. And again, it's going to take long, it's going to make your life difficult. There are more chances of errors. So as an engineer, as a person studying engineering and technology, you are supposed to use technology to help you understand and solve stuff. So let's go ahead and start working on our first circuit. In this circuit, very simple circuit. Again, think everything in terms of DC. Don't assume things are AC, although they are AC, but think DC and apply the approach that you want to apply on a DC circuit. So the source value is given to you, and then there are 4 resistors, a couple of capacitors, and then 3 inductors that are given to you. Now, when we are solving, of course, in the AC domain, in the sinusoidal domain, steady state, we're going to convert everything into complex frequency domain, that is j omega domain. So this is going to be, change my color real quick. So this is going to be V j omega, and that's going to be 20 angle 20 degrees volt. This is omega, remember, 2000, and that omega is going to be used to calculate the reactance of inductors and reactance of capacitors. So we are going to calculate reactance of each inductor, and I'm going to do it in MATLAB, so I'm not going to put, I'm putting just XL1 over here, and everyone know that XL is j omega L and XC is 1 over j omega C. So that's going to be XL2. We're going to call the reactance of capacitor XC2, XC1, and XL3. So these will be the reactance of each capacitor. The idea here is what is required of us is to determine what is the total impedance seen by the source, and we also have to calculate the total source current. So an extremely easy problem. You have to make the parallel series combination such that only one impedance is left connected across the source, and that will be the equivalent impedance seen by the source. And then we can apply Ohm's law to calculate the source current as well. So again, after you perform the analysis, basically just write down the equation, what you're looking for. So for the equivalent impedance, Z equivalent is going to be what? It's going to be, let me move this up a little bit. It's going to be XL2 in parallel to R3, XL2 parallel to R3, and then that will be in series with XL3 and R4. So XL2 parallel to R3, and they are in series with XL3, which is in series with R4. So that will be the equivalent of these components. Now that quantity is going to be connected between this node, let's call this node A, and the bottom node, if it is ground, let's say this is ground, and that will be in parallel with XC1 and R2. So this whole thing is in parallel with XC1, which is in series with R2. So we took care of all the equivalent impedance of all these quantities, all these components, and then this is going to be in series with R1 and XL1. So I'm going to put another big parentheses here, and then this will be in series with R1 and XL1. And that's our equivalent impedance. So once again, do not think in terms of numbers, think in terms of variables. And as long as you can identify which resistance, which impedance are connected in series, parallel, and their combination across the nodes between which you are trying to evaluate the equivalent impedance. Now, those nodes can be anywhere in the circuit, remember, but you have to look between those nodes as which impedance are in parallel and which impedance are in series. In this case, our node, of course, is across your source. So these are the nodes, B and ground, let's say. So between B and ground, this will be our equivalent impedance. Once again, XL2 parallel to, oh, I forgot that there is a C here as well. So R3 and XC2 are going to be in series with each other. So let me go ahead and rewrite that. So that R3, let me put, so that R3 and XC2 are going to be in series with each other. And then that will be parallel with XL2. So there's going to be, let's see, another parentheses over here. That's going to be in series with XL3 and R4. And then that combination is going to be in parallel with XC1, which is in series with R2. And then everything is going to be in series with R1 and XL. So I fixed that. I forgot this XC2 over here, but the combination of R3 and XC2 will be in parallel with XL2, which is shown over here. So let's go ahead, and I'm gonna go ahead and open my Octave, and let's go ahead and enter our numbers. So my V is, and again in MATLAB, you cannot really enter polar form of complex numbers. So I'm going to convert that number into rectangular form. So 20 times cosine d of 20 degrees plus I times sine d of 20 degrees. So that's my voltage. I think I'm missing one parenthesis. Let's see. Yeah. So that's my voltage. And now I'm going to assign all the variables. R1 is 10. L1 is 20, exponent -3. And C1 is 100 microfarad, 100 exponent -6. R2 is 30. L2 is 10 exponent -3. R3 is 5. C2 is 10 micro, -6. L3 is 5 milli. L3 is 5 exponent -3. R4 is 25. And finally, we have to give what is the value of omega, which is 2000 radian per second. So make sure you check one more time. R1 is 10, L1 is 20 milli, C1 is 100 micro, R2 is 30, L2 is 10 milli, R3 is 5 ohms, C2 is 10 micro, L3 is 5 milli, R4 is 25 ohms, and omega is 2000 radian per second. All right, after doing this, we are going to calculate the reactance of each of the inductor and capacitor. So XL1 is equal to I times omega times L1. XL2 is equal to I times omega times L2. And XL3 is equal to I times omega times L3. XC1 is 1 divided by I times omega times C1. And XC2 is 1 divided by I times omega times C2. I think we don't have C3. So these are all of my values of XL1, XL2, XL3. Oh, XL3, I put 1 instead of I, so let me go ahead and fix that. I. So XL1, XL2, XL3, XC1, and XC2. Remember, reactance of inductor is positive reactance, and then reactance of capacitor is negative because it's the denominator where you have I. So when it goes in the numerator, if you multiply numerator and denominator by the complex conjugate, then of course you're going to get negative I for the complex number. So I have all these values. I don't have to go and put the values on the circuit because I'm just going to copy and paste this. And now I'm going to go ahead and calculate my Z equivalent. Now I have my parallel function that I've been using since day one. So I'm just going to use that function. So my Z equivalent is parallel combination of XL2. So RB XL2 XL2 and R3 plus XC2. R3 plus XC2. And again, you can separate each part of this impedance and calculate it separately if it is too complicated for you. The whole thing can be calculated in a single line as I'm showing you, But as I said, you can separate, for example, you can just first calculate the parallel equivalent using the parallel function, what I'm showing you, assign it with a variable, Z1 or Z2, then add XL3 and R4 to that, assign it with to another variable, then make the parallel combination with XC1. So whichever way is easy for you, whichever way is you think you will make less mistakes, do that. Doesn't matter how you're doing it. Just make sure to use these functions, because it's just going to save you a lot of time instead of doing it manually, as most of you still do manually. But that's not an efficient way to do it. Everyone knows the formula is not going to change. I mean, parallel impedance formula is going to be 1 divided by 1 over Z1 plus 1 over Z2 plus 1 over Z3, blah, 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 1 over Z, and that is not going to change. So really, there is no pride, I would say, to calculate it manually and then getting the correct answer after 10 minutes and say, oh, I got it correctly, doing it manually. To me, that's really nothing. Everyone know how to do the division. Everyone know how to do add, two numbers and stuff. So use the functions. That's just going to help you a lot. All right, so I'm going to add into this parallel combination XL3, and then R4. And all these things, again, I'm going to take the parallel combination of this whole thing with XC1 and R2. So let's go ahead and I'm going to do this. Once again, I'm going to do parallel, put my parentheses here, okay, so this is one complete resistance. And then my second impedance is that I'm making the parallel combination is XC1 and R2. So XC1 plus R2. XC1 plus R2. And then end square bracket. So that's the parallel. This is the whole thing that is written over here. And now this will be added into R1 and XL1. So that's the Z equivalent that I wrote. And the result is in front of you, 31.798 plus 45.697. What I'm gonna do, I'm just gonna copy this instead of writing this. So let's go ahead and copy. I'm gonna copy this part first. Voltage. And then I'm going to copy the right here, starting from here, since I fixed. Oh, I also I'm gonna copy this as well, actually, this whole thing. So I'm gonna copy this whole thing, right? And then I'm gonna go ahead and copy from here. Okay, there you go. So this is my Z equivalent. So my resistance is the equivalent resistance as seen by the source is 31.798 ohms, and my equivalent impedance as seen by the source is 40J 45.697. Again, you can round that off to 45.7, and this is 31.8. So my equivalent impedance as seen by the source is an inductive reactant, the inductive impedance, because your equivalent reactance is positive. So although you have capacitors and inductor in the circuit, but when you took the equivalent of all of the components, the total reactance came out to be an inductive reactance. That means when you're creating the final circuit, this circuit, as seen by the source, is comprised of a resistor and an inductor, which is reactance of the inductor is this. We can call it R L equivalent and R equivalent. And this is your source. And now you can calculate what is the value of L equivalent. Remember, your X is j omega L. So L equivalent is the magnitude of X, that is omega L, divided by omega. So L equivalent is the imaginary part of Z. Let's do this. X equivalent is image of Z equivalent. So 45.6 image, of course, is the function in MATLAB that extract the imaginary component of the complex number. And then L equivalent will be X equivalent divided by omega. So 0.022 or 22.8 millihenry. 22.8 millihenry. So these are my two components as seen by the source. And finally, the current. The value of the current, I, coming out of the source, simply Ohm's law. I j omega is equal to V j omega over Z equivalent, which will be equal to I is equal to V over Z equivalent. 0.01922 minus this 0.1922 minus J 0.275 ampere, which is equal to, remember, since the input source is given in time domain, then you must express the current value in time domain as well. And even if it is not given in time domain, you must express all the voltage and current values in the polar form with the magnitude of the current or voltage and the phase of the current and voltage. Do not leave it in the rectangular form. So let me convert this into polar form. So that's going to be absolute of I is the magnitude, and angle of I times 180 by pi is going to be the phase. Remember, absolute value gives a square root of x squared plus y squared. That is, it calculates the magnitude of a complex number, and angle function calculates the phase of the complex number given in the rectangular form, but it calculates phase in radians, and that's why I'm multiplying it by 180 and dividing by pi to get the angle in degrees. So that's going to be 337.6 milliampere. Phase negative 55.29. Negative 55.3 degrees. 29, I'm just going to round it off to 3 degrees. And that's in milliampere. So in time domain, the current is going to be given by, therefore, IT will be equal to 337.6 cosine 2000 t minus 55.3 degrees milliamp. Since the reactance, since the circuit is, the impedance of the circuit is inductive impedance, therefore, the phase of the current is lagging the phase of the voltage. Anytime you have inductor, phase of the current lags phase of the voltage. Anytime you have a capacitive reactance, then phase of the current is going to lead phase of the voltage. So right now it is lagging. We have negative 55.3 phase of the current, and we have plus 20 degrees phase of the voltage. So if you draw the phasor diagram of this, then complex plane, this is going to be your voltage, which is 20 degrees, and what's that, 20 volt, right? 20 volt. So that's my voltage vector, 20 volt with 20 degrees, and then my current vector is going to be at negative 55. So let's say this is negative 55. And just have to show, I don't have to show negative sign. It's just the angle between the x-axis, and this is 55 degrees. If you want, you can show negative sign, because negative sign represents that you are going clockwise direction from the x-axis. Positive sign represent that you're going counterclockwise direction. So negative 55.3 degrees is this, and this is your current I with the value 300, the magnitude 337.6 milliamp. So that's a phasor diagram of the circuit, and you can draw the phasor diagram between any current value and any voltage, or between different voltages. Phasor diagram is a representation of quantities in polar form on the complex plane, represented by their magnitude and phase. So it shows how different quantities are related as far as if they're lagging each other, if they're leading each other, and what is the magnitude of each quantity. So this is the problem. Again, the problem is not difficult at all. One can make it difficult, one can assume it is difficult because the numbers are complex, but as you can see, that really I'm not doing any complex calculation with a simple calculator or anything, or with my hand. My approach is to analyze circuit, write down in the equations, and then plug in the values in MATLAB, calculate everything in MATLAB, and produce a result. So understanding is important. Calculations are important, but calculations you are doing with the help of MATLAB. If you're still using your calculator, you can, of course, I'm not going to stop you, but remember, it's going to take you maybe much longer than it's going to take you to solve this. Of course, I'm explaining, that's why I'm taking longer. If I have to do this problem without explanation, it's going to take me barely less than 5 minutes to do this, the whole thing that I'm doing this. All right. So that's problem number 1 from this set of problems. Let's look at problem number 2. If you want to take a break or something, just pause over here and then you can start working on problem number 2 when you come back. So I'm gonna keep going. So in problem number 2, let's see what has been asked. Problem number 2, use the easiest method to determine the current IC1. Okay, where is IC1? This is IC1 going through the capacitor. Now in this case, circuit is already given in the phasor form. all the phasor quantities are given in the complex frequency domain. So you do not have to convert anything from time domain to the complex frequency domain. That is LC instead of L and C reactance of those inductors and capacitors are given, as well as your voltages are also given in the complex frequency domain as phasor quantities. So what we're going to do is, again, analyze the circuit, very simple circuit. You have two sources given, and again, in the when two sources are given in the sinusoidal form, in the steady state sinusoidal circuit, we assume both sources have the same frequency. If they do not have the same frequency, then the frequency must be given for each source, and then your reactance value is going to be different for each source because reactance depend on the frequency of the source. And in that case, reactance values will not be given to you. Inductor and capacitor values will be given to you, and the sources will be given to you either in the time domain so that you know what is the value of omega for each source, or if they are given in the phasor form, then omega 1 and omega 2 or f1 or f2 will be given to you, but L and C values will be given to you, not XL and XC, because again, X and C depends on the frequency. So for each source, it's going to produce a different reactance if the frequency of each source is different. In that case, how you're going to solve it? You're going to apply superposition. So you're going to shut one of the sources down, calculate the reactance for each component according to the frequency of one of the sources, and then solve for IC1, let's say. And then you're gonna activate the other source that you have shut down and deactivate the source that was in the circuit, and then recalculate the reactance of each inductor and capacitor according to the frequency of the other source, and then calculate IC1 according to that source again. And the final result is not going to be the addition of IC1 because of each source, because the frequency is different. The final component is going to be two sinusoids, one because of VS1. So it's going to be, let's say, IC1 because of VS1 plus IC2 because of VS2. So in time domain, when you're representing that quantity, it's going to be a complex frequency quantity. That is, it's going to be a trigonometric function, but it has two frequencies. This problem, of course, is not dealing with two different frequencies. It's dealing with a single frequency, assuming that since XL and XC and XC is given to us, we assume that both sources have the same frequency, of course. That frequency is not given to us. That means we will not be expressing any quantity in the time domain. We will be just expressing IC1 in the complex frequency domain. That is, what is the magnitude of the current and what is the phase of the current IC. So again, analyze the circuit and see what is the easiest method to calculate the value of IC1. Now, many of you, again, by instinct, by the way, in this case, of course, R1 and XL1 are in series, R3 and XC2 are in series, and R2 and XC1 are in series. So these three components are in series. They will produce impedance for R1, XL1, R2, XC2, and R3, XC2. Except that if you are going to make any component in parallel, that is going to be a mistake, because in this circuit, none of the components are in parallel. So many of you are still making that mistake that you assume, let's say, Z3 and Z2 are in parallel, and then many of you add them together, and they're not in parallel. Remember, parallel means that they must be connected between the same nodes, and they are not. So actually, we also have XL2. So in this case, R3, XC2, and XL2 will be in series. So there are no parallel combination in this circuit going on. There are series combination, but there's no parallel combination in this circuit is going on. Okay, to find the easiest method. Now again, many of you look at loops and then jump to KVL, mesh analysis and KVL. Now, you can do that, yes, but that's not the easiest method. Because when you do that, you will have two equations, one for each mesh. You're going to solve for those two currents, and then current IC1 is going to be the combination of two currents. Either you're going to add them together or subtract based on the direction of the two mesh currents that you're taking. So it's not like you cannot do it, but to me that may not be the easiest method, because again, you are setting up two equations to solve. If you apply the nodal analysis, we have a single node over here. If you call it node A, we have a single node A, and if we know the voltage of that node A, then we can easily apply. And to write down the voltage, the node A voltage, we just need one equation, because all three currents are heading towards the node or going away from the node. So we can call this current I1, and we can call this current I2, and at node A, you have three currents. I1 is going towards node A, IC1 and I2 going away from node A. And you can take different directions. You can take I2 direction opposite, then I1 and I2 will be going towards node A. It doesn't really matter. The point is that KCL and nodal analysis is the easiest method to solve this problem. Once you know the node voltage A, then of course you can simply apply Ohm's law to calculate IC. And I'm going to take that route. So let's go ahead and pull up MATLAB so that we can assign all the value. Or before we pull up MATLAB, let's write down the equation of the nodal volt of the KCL at node A. So KCL at A is going to give us I1 going towards, and I2 and IC2 going, IC1 going away. And now we apply Ohm's law to write down each of this voltage in terms of the unknown voltage of node A. So I have I1 Vs1 minus Va, and I'm gonna call XL1, R1 and XL1. I'm gonna apply and call it impedance Z1, which is the series combination of R1 and XL1. And in my MATLAB, I'm just gonna call it Z1. And that's going to be I2. I2 is Va minus Vs2. And then I'm gonna call the total impedance in series as Z2, which will be the series combination of these three components. And then IC1 is simply VA. Again, we are assuming that the bottom node is grounded. VA over, in this case, I'll just call it Z3 per se, because I have Z1 over here. I have Z2, I'm calling this. So I'm just going to call this Z3, although the variables are all like R2 and C1, but let me just call this Z3. So in my MATLAB, I'm going to define the series combination of R2 and XC1 as Z3. And then, since VA is what we're looking for, then VA is going to be on one side of the equation, and everything else is on the other side of the equation. So I'm going to take this VA over Z1 on the right side, and I'm going to bring VS2 over Z2 on the left side. So I will have VS1 over Z1 on the left side, and then I'm going to bring VS2 over Z2 is going to become positive. So plus VS2 over Z2. And then on the right side, I have VA over Z1, VA over Z2, plus VA over Z3. So when I take VA as a common factor out, then I will be left with 1 over Z1 plus 1 over Z2 plus 1 over Z3. And that is going to give me my VA. So I'm going to go ahead and now bring my MATLAB up, or Octave up. Let's clear everything and clear the command window. And then let's go ahead and start putting variables. So my VS1 is 10 angle 0, which is 10. My VS2 is 5 angle 25, so 5 times. And again, instead of doing this over and over again, cosine, and sine, just in the software class, we did create that function. You can use that function that you created in the software class that can convert your polar form into rectangular form and give you as a rectangular form. So that can be used easily. I'm pretty sure I have that, but I forgot the name of that function. So I'm just gonna do cosine d of 25 plus I times sine d of 25. Just make sure that your parentheses are balanced. And then I'm just going to apply R1 is 10, R2 is 20, R3 is 44, XL1 is J10, XL2 is J29, XC1 is negative J20, and XC2 is negative 0.2I. Okay. And then I'm going to make my Z1 to be the series combination of R1 plus XL1, my Z2 to be the series combination of R3 plus XC2 plus XL2, and then my Z3 is the series combination of R2 plus XC1. So these are my Z1, Z2, and Z3 that I have defined over here, Z1, Z2, and Z3. And then all I have to do is to go ahead and calculate VA. My VA will be equal to VS1 over Z1 plus VS2 over Z2 divided by 1 over Z1 plus 1 over Z2 plus 1 over Z2. And my VA came out to be 7.0648, 2 points, so 7.06 plus J minus J, 2.75. J 2.75 volt. And I'm not converting this into polar form right now because this is not the final result. My final result that I have, that in this case I'm not gonna convert into time domain, but I'm gonna convert into polar form. But my IC is simply VA over Z3. So my VA over Z3, which is IC is VA over Z3. So that's going to be 0.2455 plus J 0.1078. So 0.245 plus J 1.107 or 0.108 or 0.108 for the 7. And now this I'm going to convert ampere, of course, ampere. And this I'm going to convert into polar form because the final result has to be in polar form. So absolute of IC and angle of IC times 185. 0.2681, so 268.1 angle 23.70. 23.7 milliampere degrees. That is going to be your final result. So once again, you can see that the whole problem actually is in one page. So, nothing once you analyze it, once you assign all the values, then the whole problem you could do in a single page. And this is all the MATLAB work that I did. So again, key is to analyze the problem properly and write down the equations properly. Forget about the values. Don't worry about the values. Values can be substituted. Once your equations are correct, basically your work is done. MATLAB, then the work that is left is for MATLAB. That it's going to take your values that you are giving, substitute them in the correct equation that you're writing, and give you the correct result. So this is problem number 2. Now let's look at problem number 3. What does it say? Okay, so two sources are given to us, VS1 and IS2. One voltage source, one current source. Both have the same frequencies. That means the reactance of each inductor or capacitor is going to be the same since the frequency is same. Values of each one of them are given to us, and we have to determine the voltage across C1. So C1 is this, so we have to find the voltage across C1 and the current passing through L2. The current passing through L2. So we need to know C1. And we can assume one direction, in which direction we want to show C1. Of course, it's a sinusoidal quantity. It will keep changing its direction. But let's say you want to show the C1 in this direction. VC1. And remember, this will be a time domain quantity that you have to give. And then, of course, the current. Again, current will keep changing its direction as well because it's a sinusoidal quantity. But I want to show, when I'm calculating, I want to show that my current is this that I'm trying to figure out. So these are the two quantities that we need to calculate. Okay. So again, let's analyze. Of course, first we're going to convert everything into polar form. This is going to be VS1 j omega, which will be 20 angle 0 degrees volt. This is going to be IS2 j omega, which will be 0.1 angle 25 degrees ampere. And then, of course, C1 will convert that into XC1. That's going to be XL1. And this is going to be XL2. And this is going to be XC2. So we will convert all the capacitors and inductor into their respective reactance values. Now, in this case, R1 and XL1 are going to be in series, of course. But they will not be in parallel with XC2 and R2 because of this node that we have here. XC2 and R2 will not be in series either. R3 and L2 are in series, of course. So how are we going to find VC1 and IL2? You can apply, again, the easiest method. We have to apply the easiest method. You can apply either KVL and mesh analysis, or you can apply KCL and nodal analysis. Now, which one is going to give you less number of equations? If you go with KVL and mesh analysis, then you have, of course, this mesh. Let's call it mesh number 1. You have mesh number 2, and then you have mesh number 3. Now, out of these 3 meshes, mesh number 3, we already know the current because that's the current of the current source. So we already know the current of mesh number 3. Mesh number 1 and mesh number 2, we will have to apply KVL and mesh analysis and establish two equations to calculate the current in those two meshes. Once we have the current, of course, we can apply Ohm's law to calculate the voltage across C1, and then IL2 is going to be either the sum of the mesh current 1 and IS2 or the subtraction of that based on the direction that you're taking. So two equations for mesh analysis. Now, if you apply nodal analysis, let's see. In nodal analysis, we have, of course, this node. Let's say node, let's call this node A, node B, and node C. We're not going to take this node because they are in series anyways. Okay, out of these three nodes, node A voltage we already know because that's the voltage VS1, so we don't really need to apply nodal analysis at node A. Remember, if you know the node voltage, you don't apply the nodal analysis at that node. Node B voltage we do not know, so we have to apply the nodal analysis, KCL first and nodal analysis. And likewise, node C voltage we do not know, so we have to apply the KCL and then the nodal analysis. So in this case, again, we have two nodes. So two equations. So two equations for nodal analysis, two equations for mesh analysis. Your choice, because both you will have to establish two equations. Many of you are comfortable applying KVL and mesh analysis. Let's just go with that then for this, because we apply the nodal analysis in problem number 2. So in this case, we can apply KVL and mesh analysis instead of KCL and nodal analysis, because in each case, we are going to get two equations. And then we have to solve for those equations to either find the loop currents or mesh currents or the node voltages. And once we know those, nodal voltages or mesh current, then we can easily find the required quantities, which is the capacitor voltage C1 and the inductor current IL2. So in this case, I'm going to go KVL and mesh analysis. So KVL in loop 1. When we apply KVL in loop 1, the equation is going to be, of course, VS1, and let's assume that we have to show, of course, in which direction we are taking our current. So let's say I'm taking my current in this direction. Let's call this current I1. We already have current IS2 in this. We don't have to apply KVL in this. And then again, you can take whichever direction you want in this. Let's say I take, and let's call this current I2. So I'm going to go ahead and apply KVL in mesh number 1, and that's going to be VS1 is equal to I1 minus I2 times XC1, and then I1 plus IS2 times R3 plus XL2. That is going to be the equation for this. So, oops. So VS1 is equal to I1. Let's see, I1 is flowing through how many components? I1 is flowing through XC1, R3, and XL2. So R3 plus XL2 plus XC1. And then the current I2. So XC1, XL2, and R3. Current I2 is in the opposite direction than X1, so we're going to take it as negative. So that's passing through in this loop through XC1. So minus I2 XC1. Minus I2 XC1. And then we have the third current, which is IS2 passing through R3 and XL2 in the same direction as I1. So that's we're going to take it positive. So plus IS2 R3 plus XL2 plus IS2 R3 plus XL2. Okay. All right, all known quantities on one side and unknown on the other side. So I1 R3 plus XL2 plus XC1 unknown, and I2 is unknown. Minus I2 XC1. And then the known quantities are VS1 and IS2. So minus, when I take it on the other side, it's going to become negative IS2 R3 plus XL2. And that's my equation number 1. So again, everything in terms of variables. And then I'm going to apply KVL in loop 2. And KVL in loop 2 is going to give me an equation. Let's start with I1. So I1 and I2 are in the opposite direction. I2 is now supposed to be the positive, the current. So I1 is opposing it. So I'm going to have negative I1 times XC1. Negative I1 times XC1. And then I2 is positive plus I2. And I2 is passing through 4 components, R1, R2, XL1, and XC1. R1 plus R2 plus XL1 plus XC1. And then I have the third current, which is IS2, which is passing through R2. And IS2 and I2, and they pass through R2, they have the same direction. So I'm going to put plus IS2 times R2 plus IS2 times R2. And there is no source in loop 2, so S equal to 0. And once again, no quantities on one side, minus I1 XC1 plus I2 R1 plus R2 plus XL1 plus XC1. And the known quantity is negative IS2 times R2. And that is my equation number 2. So once I solve these 2 equations, I'm going to find the values of 2 loop currents. And once I have those 2 loop currents, of course, I can easily find the value of capacitor voltage 1 and inductor current. So let's go ahead and open my MATLAB one more time and start plugging in the values. So R1 is 100, L1 is 0.1, C1 is 1 micro, exponent negative 6, R2 is 220, R3 is 333 ohms, L2 is 10 exponent negative 3, 10 millihenry, C2 is 0.5 microfarad. So C2 is 0.5 exponent negative 6. So I have R1 100, L1 0.1, C1 1 micro, R2 220, R3 333, L2 10 millihenry, and C2 0.5 microfarad. And then I have 2 sources. So source number, I'm going to go to the next slide. Source number 1, VS1. VS1 is 20 angle 0, so I'm just going to call it 20 volt. And then IS2 is 0.1 angle 25, so 0.1 times cosine D of 25 plus I times sine D of 25. So those are saved in my MATLAB. And one more thing, omega. Of course, omega is 2000 pi because we have to calculate the reactance of each component, 2000 times pi. which will give us XL1 equals, let's do it on the other line, XL1 equals I times omega times L1. XL2 is equal to I times omega times L2. And then C1 and C2. L1 and 2 here. So XC1 is equal to 1 divided by I times omega times C1. And XC2 is equal to 1 divided by I times omega times C2. So these are all the values of the reactants, right? And now I am ready to evaluate my I1 and I2. So let's say my constant vector, that are the coefficient, sorry, not the constant vector, the coefficients of current I. The coefficients from the first equation is R3 plus XL2 plus XC1. That's the first row, first column. The first row, second column is negative XC1. And then the second row and the first column is negative XC1. And in the second row and second column is R1 plus R2 plus XL1 plus XC. So that's my matrix with the coefficients of I1 and I2 from the two equations. And now my vector on the right-hand side, constant vector, let's call this K. My constant vector from the first equation is Vs1 minus Is2 times R3 plus XL2. Okay. And my second row is negative R2. Negative R2. So this is my constant vector on the right-hand side. And my current I is using the inverse matrix method, A divided by K. So these are my two current values, I1 on top and I2 at the bottom. Okay, I'm gonna go ahead and I'll copy it later, but I'm gonna just go ahead and write down these. Let's see. I'll just copy and paste like this. Solving 1 and 2 simultaneously. That is, so this is my I1 j omega, and this is my I2 j omega. Now in this case, I1 and I2 are not our final results. So you don't really have to convert that into polar form. You can just leave them in the rectangular form. Only the final result you need to convert into polar form. So these are not my final results. Now, we know I1 and I2 now. So we can easily find IL2, which is a combination of I1 plus IS2. And the voltage across capacitor 1 is simply Ohm's law, which will be I1 times XC1. So very simple. Let's go back to my drawing. Therefore, IL2 is IS2, therefore it has to be implies, which implies IL2 is equal to IS2 plus I1, and VC1 is I1 times XC1. Okay, let's go ahead and calculate that. IL2 is I of 1. I have not assigned the values of the vector, as the first value is I1 and the second value is I2. So I'm just going to call the first value as I of 1, of course, as my I1. I of 1 plus IS2. So that's my IL2. Now this has to be given in polar form. So I'm just going to do absolute of IL2 absolute of IL2. We can also use polar to rectangular. I guess it was a polar to rectangular, polar to Cartesian, whatever the function was. We can also use that, but I'm just going to use absolute. 0.2185, and then angle of IL2 times 185, 32.879, and my VC1 is I of 1 times XC1. So once again, absolute value of VC1 is the magnitude, and angle of VC1 times 185. Let's go ahead and put these over here. Equals where is it? IL2. Okay, so it is 0.1835 plus J 0.118. So I'm going to write down 0.183 or 184 plus 0.12. We can do 0.183. J 0.118 ampere, which is equal to, I'm going to put down absolute value is 0.2185, angle is 32.88. 0.218, angle 32.8 degrees. And likewise, my capacitor voltage is 12.148 minus 14.774, 12.14 or 12.148 minus J, 14.77, which is equal to, in the polar form, 19.127 angle negative 50.5. 19.127 angle negative 50.5, right? 50.57. 50.6, you can write down 50.57. So these are my two required quantities. Again, very simple-ish problem. If I do not have to explain it step by step, then again, problem should not take more than 10 minutes, I would say. I'm going to go ahead and copy my MATLAB work as well. Okay, so that is all the work that I have done for this problem. And the problem is again a straightforward problem, and this could be solved using either KCL and nodal analysis or KVL and mesh analysis, whichever you think you can do better, because both methods are going to give you the same number of equations. And if you're using MATLAB, of course, irrespective which method you're using, it's all the correct, the setting up the correct equations, because solution is we are doing through MATLAB. So that's not an issue. But the important thing is that you set up the correct equation. So we have done KVL and mesh analysis here. I think it's going to be really good for your practice to do KCL and nodal analysis and then see if you get the same result as we are doing in this problem. And if I may, if I make a mistake anywhere, but if I'm taking that mistake until the end of the problem, then my results are going to be according to that mistake that I made. So results may be incorrect. However, the method is still going to be correct. So remember, method is a lot more important. The correct method, that is a lot more important. But if I made a mistake of any value I didn't put correctly, I usually check my values a couple of times. But if I forget some value or something, then it's possible that my result is incorrect. But again, my approach is still going to be correct. Okay, let's do problem number 4. Is this our last problem? No, we have problem 5 as well. Okay, so let's do problem number 4 and then problem number 5. Again, you can, this is going to be a long video, so you can watch it in parts. You can watch each problem in one sitting or a couple of problems in one sitting. But before you watch them, again, solve these problems yourself and then watch the lecture so that you can see, you can really learn. Because if you just watch it, just watch me solving it, you're not going to learn anything, basically. If a problem comes in front of you and the solution is not there, or if somebody is not solving in front of you, then you're going to struggle for sure. So solve it first, then watch this lecture. All right, problem number 4. Use the easiest approach to find which quantities? IC1 and VC2. So this is IC1 and VC2. Okay, again, observe the problem for a minute before you jump into a specific method that you want to apply. Observe as what will be the easiest method and how you're going to find the two quantities that are required. So many of you, again, when you see loop, you guys jump instantaneously into solving it with loops. This problem can be solved using basically simply combination of resistors, impedance in this case. So you can combine all the impedance, and then you can have only R1 and an equivalent impedance and your source. The source current will be going through that one loop. So you can find the voltage across your impedance. That voltage is going to be valid across XL1 and R2, XC1 and R3, and R4, XL2, and XC2. That will be valid, right? And then you can apply Ohm's law to calculate IC1, which will be the voltage that you will find here at this node. Let's call this node A, the voltage that you will find at node A. And then you can apply voltage division to find the voltage across XC2, again, because the total voltage across the series combination of R4, XL2, and XC2 is going to be the node voltage A. So that looks like a very straightforward method to find these two quantities, IC1 and VC2. No need to go into the loop analysis. Second thing that you can do, loop analysis, of course, if you apply, we already know the current in this mesh or loop, so you don't really apply here. But many of you may think, okay, we have these two loops, we apply the current, we apply the KVL and mesh analysis and find the unknown current, and again, it's going to take longer. Second thing that can be done is to find the voltage of node A directly. without the combination of resistor, applying the KCL and nodal analysis, because there's only one node. So you can apply, you can write down the KCL equation at node A, and then apply nodal analysis to find the voltage at node A. And then once you have the node voltage A, then again you can apply Ohm's law to find IC1 and voltage division to find VC2. Whichever way you want to do it, I think both ways are very straightforward. You want to do combination of impedance or you want to do nodal analysis. I think both are straightforward, whichever way you want to apply. Let's go ahead and apply the nodal analysis method, let's say. So we call this current is IS, of course, going towards node A. Let's call this current I1 going away from node A. And then let's call this current IC2 going away from node A. So we can write down KCL at node A. So again, the basic idea is to find the voltage at node A. Again, you can use combination of impedance, perfectly fine, and then go from there, or you can apply KCL and nodal analysis. Again, it's going to be only one equation to do node A. So KCL at node A is going to give me IS equals, let's see, IS equals I1 plus IC1 plus IC2. I1 plus IC1 plus IC2. IS equals I1 is VA over XL1 and R2. VA over, and again, if I go ahead and take the combination of resistor as Z1, this is as Z2, and these three as Z3, then I can just do VA over Z1, VA over Z2, and VA over Z3. And then I can define those Z1, Z2, Z3 in my Octave. VA over Z1, VA over Z2, and VA over Z3. Once again, this is a short node, remember. It's a short circuit. You can just put this node right over here. You don't have to show this short. I know many of you get confused when you see this short and you will start applying a current in here as well. This current is basically, that is coming over here, is the combination of IC1 and IC2. So you don't have to show this short if you don't want to. You can just connect this node at A, because this is A basically. Both of them are node A. There's no difference between the two nodes. Okay, so that's going to be VA over Z1, VA over Z2, and then VA over Z3 as my three currents that you see over here. And then from there, my VA will be simply IS over 1 over Z1 plus 1 over Z2 plus 1 over Z3. So let's go and plug in stuff in MATLAB. My IS is 2 times cosine D of 15 plus I times sine D of 15. 7 times sine D of 15, and my R1 is 100 ohms. It's 100. My XL1, we're really not using R1 anyway, so 200I. R2 is 60, and I'm going to define my Z1 as R2 plus XL. So R2 plus XL1. That's my C1. And then I'm gonna go and define my XC1 as -50I, and R3 is 66 ohms, and my Z2 is R3 plus XC1. And my last set of components, R4 is 120 ohms, XL2 is 67 ohms, and my XC2 is 120, -120 ohms. And that will make my last impedance Z3, which will be the combination of R4 plus XL2 plus XC2. So that's my Z3. And once I have all these, then I can just go ahead and calculate my node voltage. VA is IS divided by 1 over Z1 plus 1 over Z2 plus 1 over Z3. So 105.78 minus J 5.24. 105.78 minus J 5.24. 5.25 to round this off. Volt. Once again, there's no need to represent this into the polar form because this is not our final answer. Our final result is IC1 and VC2. So IC1 is VA over Z2. That's our Z2, XC1 and R3. VA over Z2. And VC2 using voltage division is VA times XC2 divided by the series combination, which is C3. VA times XC2 over Z3. And this is my voltage division. Voltage division, this is simply ohms. So let's go ahead and calculate these two quantities, and these are our final answers. So we're going to represent these two quantities in polar form. Okay, so IC1 is VA over Z2. And let's see, pole direct. I think I do have the function pole direct. Let's say R comma T is equal to pole to rect or pole rect. I have a couple of functions that I wrote down, maybe pole rect. Pole rect of IC1. Let's see if I have this function. Nope, I don't have pole rect function. So let me just go ahead and then maybe have a pole to rect. Pole to rect. Oh, okay. Never mind. So I'm just gonna use my regular I absolute of IC1 is the magnitude, and angle of IC1 times 185. I have those functions written, but maybe not in this MATLAB folder that I'm using. But you can always use MATLAB built-in function. I think that's pole to car. No. Oh, actually, I'm using incorrect function anyways. It's rectangular to polar. That's what we have to do. Rect to pole. Or in MATLAB, I think it's rect to car.
No, it's card to pole. I forgot the function in MATLAB, the built-in function, but I wrote a few functions anyways. So that's 1.05 plus j 0.72, 1.05 plus j plus j 0.72 ampere, which is equal to, in polar form, 1.28 angle 34.3, 1.28 angle 34.3, right? 34.3 degrees. So that's my IC1, and likewise, let's calculate VC2 using voltage division. VC2 is VA times XC2 divided by C3. 34.7 minus J, 90.45. 34.7 minus J, 90.45 volt. And then we're going to convert that into polar form. So absolute of VC2 and angle of VC2 times 180 by 96.8, angle negative 69.0. 96.8 angle negative 69.0. So these are our two required quantities. And once again, you saw how simple it is to solve it. As long as you're not putting numbers right from the get-go, it's just all analysis. That's how you're going to do it. And then plugging in the numbers in MATLAB. That's it. So that is your work. All right, so this is problem number 4. And again, if you want to take a break, please feel free to take a break. It's a long lecture. We have 5 problems. And once again, solve each problem before you watch the solution. Calculate VL1, that is across XL1, and IR3, that is current flowing through R3, using the easiest approach. If the frequency of the circuit is 60 Hertz, determine the two quantities that you calculated in the time domain as a time domain expression as well, both of them. So again, analyze the circuit first. Circuit is already given in phasor form. So you don't have to convert inductors and capacitors into reactance. They are given to you. It also has a dependent source. And the dependent source is half of the current IR1 that is passing through R1. Okay, the question is VL1, of course, if you know the current passing through XL1, or if you know the voltage at that node, then you know what is the voltage across XL1. As far as IR3 is concerned, if you know the voltage on the top node between R4, R2, and XC1, then you can apply Ohm's law to get IR3. Now, we have two nodes, and we can apply nodal analysis to get voltages of those two nodes. That's one way to go about this problem. The other way to go about this problem is in the middle loop, the loop current is ID. In the right loop, we don't know the loop current. In the left loop, we don't know the loop current. So we have two loops, two meshes with unknown currents, and we have the middle loop with the known current, although again, the middle loop, the current is dependent source. We don't really know the exact value of the current because it depends on IR1. But the loop current 1 is IR1 anyways. So if we know that current, we will know the ID. So the question is, again, it all comes down to you. Easiest approaches can be nodal analysis, can be mesh analysis, because in either case, you are going to get two equations. So again, it's your call what you want to apply. And I know most of you are comfortable with mesh analysis, and you're most likely are going to apply mesh analysis. Where you can make mistake is identifying the fact that the middle loop, you don't have to apply mesh analysis because you already know the current of that, and substitute IR1 as the mesh current for the left mesh. You can call that current IR1 if you want, keep it as IR1. And because that's the current in that the coming out of the source anyways. So, and in the right mesh, you can assign a current, whatever you want to call it. It's not IR3, by the way, because IR3 is the branch IR3 is common between the two meshes. So IR3 is not the mesh current. It's not the mesh current of the right mesh, and you can call it I2 or IR4, whatever you want to call it. Just assign a variable. Let's go ahead and apply mesh analysis then, since most of you will be doing it anyways. And then your exercise is going to be to apply nodal analysis and see if we can find the same current values. So in this mesh, I already have in mesh number 1. In mesh number 1, I already have the current IR1. In mesh number 2, I have the current ID. And in mesh number 3, I can assign a current, and that current can very well be I don't have any I1, but going with VS2, I just want to call it IS2, the current coming out of the source, VS2. So let's say these are our three currents. And we can go ahead and write the KVL equation for mesh 1. KVL in loop 1. And that KVL equation is going to be VS1 is the voltage, IR1 is the current, which is passing through R1 and XL1 in the clockwise direction, and ID direction is opposite of that. Remember, ID is flowing in this direction. ID. So that is opposing IR1. So I'm going to write this down. VS1 is equal to IR1, R1 plus XL1 minus ID XL1, right? It's passing through XL. So ID times XL. From which ID is half times R1. So actually I can find IR1 value from here without setting the linear equations and solving them simultaneously, because ID is half times IR1. So VS1 is equal to IR1, R1 plus XL1. ID is half times IR1 XL. So we can go ahead and calculate IR1 as Vs divided by R1 plus XL1 minus half XL1. So XL1 just minus half XL1, which is Vs over R1 plus 0.5 XL1. So that's going to be my IR. Okay, once I find IR1, I still need to find, of course, IS2 in order to find IR3. So let's write down the KVL equation for loop 3. So keep some space so that when I calculate IR1, I can write it down. KVL. Okay, KVL in loop 3 is going to be my source is VS2. So VS2 is equal to IS2 times these four components, XC2 plus R4 plus XC1 plus R3. And then ID is going in the same direction through XC1 and R3 as IS2. So it's going to be plus ID XC1 plus R3. R3 plus R4 plus XC1 plus XC2. R3 plus R4 plus XC3 plus XC1 plus XC2. C1 XC1 plus XC2. And then ID times XC1 plus R3. R3 plus XC1. And of course, we will know the value of ID since ID is half times IR1. So once we know IR1, we will know the value of ID. That means that's a known quantity now, which will make IS2 to be equal to VS2 minus ID times R3 plus XC1 divided by R3 plus R4 plus XC1 plus XC2. So now I have all the equations to calculate my two loop currents, and when I have two loop currents, it's very easy for me to find the required quantities, that is my voltage across XL1 and my current passing through resistor 3. Okay, let's see. VS1 equals 10, R1 equals 220, XL1 equals 120i, and R2 equals 100. We're not really using R2 anyways. XC1 equals negative 100i. R3 equals 150. R4 is 600 ohms. R4 is 600 ohms. 600. XC2 is 177, negative 177i. And finally, VS2, let me do it on next line. VS2 is 7 angle 77, so 7 times cosine D of 77 plus I times sine D of 77. So let's double check. VS1 is 10 volt, R1 is 220, XL1 is 120I, R2 that we are not using is 100, XC1 is negative 100I, R3 is 150, R4 is 600, XC2 is negative 177I, and VS2 is 7 times cosine of 77 plus J sine of 77. So all the values seems to be correct. So let's go ahead and then calculate IR1. IR1 is VS, I think it's VS1, right? Yeah, it's VS1. Instead of VS, that's VS1. VS1. Let's make sure that I'm writing it VS1. Yeah, it's VS1. So VS1 divided by R1 plus 0.5 times XL1. Okay, so that's my IR1. Again, this is not my final result, so I'm not going to show it in the polar form. I'm going to keep it in the rectangular form. I can just write down the result. 0.042 minus 0.01. 0.042 minus 0.01 J ampere. Okay, and then my ID is 0.5 times IR1, so I'll keep that here, right? ID is half IR1. And then I'm going to calculate my next current, which is IS2. IS2 is VS2 minus ID times R3 plus XC1 divided by R3 plus R4 plus XC1 plus XC2. Okay, negative 5.44 exponent negative 3 plus 1.10 exponent negative 2. So if I write this down both in milliampere, the second quantity is going to become, or I can just do format show G, and IS2 is negative 5.44 plus J 11.05 milliampere. Negative 5.44 plus J 11.05 milliampere or 0.6 milliampere, whatever you are, 0.6 milliampere. Again, this is not our final result, so no need to convert this back into the polar form. The final values you need in the polar form because we also have to express those values in time domain. And so my VL1, the current that is passing through XL1 is IR1 minus ID. And that times XL1 will be VL1. So this implies VL1 is equal to IR1 minus ID times XL1. And this I'm gonna express both in the polar form and rectangular form. And my current passing through R3, IR3 is the combination of the two loop currents, loop 3 and loop 2, IS2 plus ID. Because they are passing through R3 and XC1 in the same direction from top to bottom. So IS2 plus ID. IS2 plus ID. And again, this we are going to express both in the polar form as well as, rectangular form as well as the polar form. So VL1 equals IR1 minus IT, absolute value of VL1, and then angle of VL1 times 185. Okay, let's write this down. So that is 21.15 minus 5.7 millivolt. 21 point, wait a minute. No, I made it. Oh, I did not multiply that by Excel. So back. Times XL1. Okay. So 0.692 plus 0.253. 0.692 plus J 2.53 volt, which in polar form, absolute of VL1, 2.63, angle of VL1 times 185, 74.74 or 75, 2.63, 74.74, 2.63 angle 74.74 degrees. And now my current passing through R3, IR3 is IS2 plus ID absolute of IR3 and angle of IR3 times 180. Okay, 15.70 plus J, 5.28 milliampere, 15.70 plus J, 5.28. 15.70 plus J, 5.2, I'll just say 9 milliampere, which is equal to 0 plus J, 5.29 milliampere, 16.57, angle 18.6, 16.57, 16.57, angle 18 degrees, 18.6 degrees, 18.6 milliamp. All right, and now, so these are the values in the, of course, phasor form, but we also have to represent these values in time domain when the frequency is given to us. And the frequency that is given to us is 60 hertz, corresponding to 60 hertz. Since f is equal to 60 hertz, omega is equal to 2 pi f is going to be 120 pi radian per second. So my VL1 in time domain is going to be 2.63 cosine 120 pi t plus 74.74 degrees volt, and my IR3T will be equal to 16.57 cosine 120 pi t plus 18.6 degrees. And these are the final results.